Welcome to all of you in Sankalpa Education Pratham classes. I am Sachin Patil, delivered lecture series on rotational dynamics. Right now we are going with the moment of inertia of uniform ring. Let us consider mass m of ring uniformly distributed at distance equal to radius r from axis and m with the mass of that ring, and it is uniformly distributed from the axis of rotation or axis at a distance r, and therefore the moment of inertia of that ring is given as mr square. Mr square is the moment of inertia because total mass m is distributed from the axis of rotation at uniform or same distance. Distance is nothing but a capital R. It is nothing but a radius of that ring, and therefore moment of inertia of ring is nothing but I is equal to mr square is here. Now we see that the moment of inertia of uniform ring is nothing but which having the mass m and radius r is nothing but I is equal to mr square. Right now we are moving with the moment of inertia of uniform disk. That means the disk having the radius r is here and axis passing through the center O, and we know that the disk having the very small thickness, and therefore the thickness of that disk is not considered or neglected here. And right now the disk is nothing but it is a concentric rings which are moving from center to the up to radius of that disk, and therefore the disk is made up of lot of rings which started from the center of that disk and moving toward the radius of the disk, and therefore you have to consider here at a distance r one ring having the width is nothing but a dr, and r with the radius of that uniform disk is here. Let us consider it is a two-dimensional circular object with negligible thickness. And right now we have to consider it is a uniform one, and therefore you will get the surface density. What does it mean? The surface density is nothing but a surface density. It is denoted by sigma, and it is nothing but a mass divided by area. We know that there are three densities are there. One is a surface density, which is nothing but having the definition mass per unit area. Another one is a linear density, which having the equation or having the definition is mass per unit length is there, and we have to use the normal density, which is nothing but a mass per unit volume is there, and therefore surface density is nothing but a sigma. It is denoted by sigma. This is letter sigma, and which is having the mass per unit area. Let us consider m be the mass of that disk and area be the A, and it is a constant everywhere because we have to consider our disk is a uniform one, and therefore let r be the radius of disk, then A is equal to pi r square, because we know that the r be the radius of the disk, and therefore area of circle is nothing but the area of that disk, and which is given as A is equal to pi r square, and therefore sigma is equal to m divided by pi r square is here. Right now we will get the sigma is equal to m divided by pi r square. Disk consists of number of concentric rings. That means disk is made up of number of concentric rings start from center O of disk and end at radius R of disk. And therefore you will get the consideration of you will get the consideration of the disk is made up of lot of rings which is started from the center and goes up to the radius of that disk. And therefore let us consider small mass dm be the small mass and dm be the small mass of the one ring which having the dr be the width of ring at with radius small r. And therefore you will get the consideration of area of that ring is equal to, let us consider this area is nothing but a, and which is given as 2 pi r into dr. And therefore sigma, that means density, surface density of that ring is given as dm divided by, that means mass per unit area, and dm divided by 2 pi r into dr. And we know that the moment of inertia of that elemental ring, that means a small ring which is considered at a radius r from the center of the disk, this moment of inertia of elemental ring, that means considered ring, elemental ring, or also it is called as a considered ring, is nothing but according to moment of inertia of uniform ring is given as mr square. And right now we have to consider one ring is here, and the ring having the mass dm and radius of that ring is r, and therefore the moment of inertia of that elemental ring is dm into r square. And therefore moment of inertia of disk can be calculated by using integration taking from 0 to r. That means 0 is work as a lower limit and r is work as a upper limit. Therefore we have to take the integration or moment of inertia of the disk. Moment of inertia of disk is equal to integration from 0 to r, that means r is work as a lower limit and capital R, 0 is work as a lower limit and capital R is work as a upper limit, and dm into r square. Right now we know that the but we have sigma is equal to dm divided by 2 pi r into dr. It implies that dm is equal to, we have to take the, this is a divide here and you will take the multiplied here, and therefore dm is equal to 2 pi r into dr into sigma, and this value of dm put it inside the integration, you will get the moment of inertia of disk is equal to integration 0 to r 2 pi r into dr into sigma, and this r square is here, r square into r, that means r cube. You will get the consideration of 0 to r 2 pi r cube into dr into sigma. Right now the sigma, it is related to surface density, which is a constant everywhere because our disk is uniform. 2 pi is a constant, and therefore those constant are taking outside from the integration. 2 pi sigma are taking outside and taking integration 0 to r, taking integration 0 to r cube into dr is here. Right now we have to take the consideration of 2 pi into sigma. The integration of r cube into dr is nothing but r raised to 4 divided by 4, and lower limit is taken here and upper limit is taken here. Here we since that integration of x raised to n into dx is equal to x raised to n plus 1 divided by n plus 1 is here, and by using this formula you will get the integration of r cube dm is nothing but r raised to 4 divided by 4. Now putting the upper limit and lower limit and taking the subtraction of these two value, you will get the integration of this one 2 pi sigma inside the bracket capital R raised to 4 divided by 4 minus 0 raised to 4 divided by 4. 0 raised to 4 divided by 4 is nothing but a 0, and therefore you will get the 2 pi sigma R raised to 4 divided by 4 is here. Now we have to cancel out this 2 and 2 to 4. You will get the pi sigma into r raised to 4 divided by 2 is here. Right now we have to know about that the consideration of sigma for disk. Sigma for disk is nothing but since sigma is equal to m divided by a, that means m is nothing but a mass of the disk, uniform disk, and a is equal to pi r square is here, and therefore it implies that m is equal to sigma into pi r square, sigma into pi r square. Now we have to adjust those values like that one. You will get the consideration as pi into sigma into pi into r square divided by 2. R raised to 4 is divided into two quantities, that means r square into r square, and sigma pi r square is nothing but a m, that means the mass of that disk m r square divided by 2 is here, and this is the moment of inertia of disk is here, and this is the moment of inertia of disk is calculated by using integration, because we have to consider the disk is nothing but a homogeneous material of concentric rings started from the center of disk to the radius of the disk, and you will get the integration is nothing but a summation which is taken from the 0 to r is here, and therefore you will get the moment of inertia of disk is mr square divided by 2. Now we are moving with the next consideration is nothing but a radius of gyration, and the radius of gyration we know that the moment of inertia depends on first is mass of individual particle, and second is a distribution of mass from axis of rotation. We have to take the consideration like that axis is here. I'm using it in short one. This axis nothing but a rotational axis or axis of rotation is here, and as per distribution of mass we express moment of inertia as I is equal to mk square is here, and that is mass of object is effective at a distance k from axis at that time k is called radius of gyration, that is the distance from axis of rotation to the point at which whole mass of the body supposed to be concentrated or effective is called radius of gyration. And we know that the larger the value of k, then farther or farthest the distribution from axis is here. For example, we have to consider here, for example, let m is a mass of ring as well as disk, r be the radius of both, that is ring and disk also. And at that, let have to consider, let IR and ID be the moment of inertias of ring and disk respectively. And therefore you will get the IR is equal to, we know that the moment of inertia of ring is equal to IR is equal to mr square. It is equal to, later to consider, here we will take the mass is a small m, later to consider it is considered as a mass capital M, and therefore capital MR square is equal to mkr square, and it implies that kr is equal to capital R. Right now for the ID moment of inertia of a disk is nothing but mr square divided by 2. It is equal to mkd square, and it implies that kd is equal to capital R divided by root 2. From these two equations, that means kr is equal to R and kd is equal to R divided by root 2, you get we get kd is less than kr. It shows that k decides the distribution of mass. It shows that k decides the distribution. K decide by distribution of mass. That is in ring, mass distributed at distance r from axis, whereas in disk mass distributed from 0 to r distance from axis, and therefore it shows that the k decides or decided decided by the distribution of mass. The k distribution of mass is smaller at that time, k is smaller, and distribution of mass is larger at that time, k is larger. That means when a large value of k, then farthest the distribution of mass from the axis, and when a small value of k, it shows that the distribution of mass is very close to the axis of rotation. And this is the consideration related to that radius of gyration is here. If you like this video, then please subscribe my channel and press the bell icon to get the notification to the lecture series related to rotational dynamics. Thank you.